Well, hey everybody. This is just going to be a video about eigenvalues and eigenvectors, and we're going to practice finding the eigenvalues and eigenvectors of several matrices, and talk a little bit about defective and non-defective matrices, some of the stuff that is a crucial part of linear algebra. Throughout this discussion, there's going to be a matrix involved, and its size is n by n. It has to be a square matrix. So everything we're going to say in this video is for square matrix only. And just to define again what an eigenvalue and an eigenvector are, this equation right here, AV equals lambda v, is the key. Okay, it's the most important thing here. So the idea is you have a vector v, which I'll just visualize that way. Okay, and if when you multiply the vector by the matrix, right? By the way, this is a vector. Let me just clarify. This is a vector in Rn. Okay, when you multiply that matrix, that vector by the matrix A. So notice what you're doing. You're taking an n by n matrix times an n by 1 column. You're going to get another n by 1 vector. And if that vector happens to just be a multiple, a scalar multiple, lambda times v, then your vector is an eigenvector. All right? And the corresponding scalar multiple, which is kind of like the stretch factor, that's what we're calling lambda here. Okay? So this picture just shows what's going on. Remember, the matrix is taking the vector and it's doing something to it. It's like a function. The matrix is a function. It takes the vector v and returns another vector, which is a times v. And if that vector that is returned is just a multiple of v, then this equation represents what happens, and lambda is an eigenvalue. It's just some number, right? It's the stretch factor. And v is the corresponding eigenvector. Okay? Just as a matter of convention, eigenvectors have to be non-zero. Okay? So 0 is never allowed as an eigenvector. Okay? So the question is going to come up right away. How can we find the eigenvalues and eigenvectors of a matrix? So the way to do that is to first figure out what are all of the eigenvalues. Okay? So there's a series of statements here on the board that essentially tell you how you're going to find those eigenvalues. Lambda is an eigenvalue of your matrix precisely when there is a non-zero vector such that AV equals lambda v. All right? I can rewrite that by subtracting everything to the left side of the equation, and I'll get A minus lambda I times v equals 0. That means that the vector v is being killed by the matrix A minus lambda I, whatever the lambda is and whatever the v is. Okay, so this eigenvalue-eigenvector pair has this property that A minus the eigenvalue times I is the identity matrix. When you apply that to the eigenvector v, it gets killed. In other words, v is in the null space of A minus lambda I, right? V is in the null space of A minus lambda I. Well, whenever you have a non-zero vector in the null space of a matrix, then that matrix cannot be invertible. You can go back to the invertible matrix theorem and review that point. An invertible matrix has no null space. It has a trivial null space. So if there is an eigenvector in the null space, well, then that's not an invertible matrix. Okay? A minus lambda I would not be invertible. And of course, going back to our way of checking for invertible matrices, we use the determinant. So the determinant of A minus lambda I for a non-invertible matrix would be 0. Okay? So the way you find your eigenvalues is you solve this characteristic equation, as it's called, for lambda. Okay? Let me show you a very quick example of that. I'm going to put it right here. I did one before, but let me just do a simple one here. Let's take A to be the following 2 by 2 matrix, 1, -3, and 1, 5. Okay? Let's find the eigenvalues. Find the eigenvalues of A. Okay? Let's find the eigenvalues of this matrix. So let's see if we can do that. We're going to use the characteristic equation. Okay? So I'm going to take the determinant of A minus lambda I. What that means is that we're going to subtract lambda from the main diagonal entries. Right? We subtract lambda there, and then we leave the other entries alone. Okay? This is just a 2 by 2. So for a 2 by 2 matrix, finding the determinant is not too difficult. We're going to get, what, 1 minus lambda times 5 minus lambda, and then plus 3. Okay? My characteristic equation is going to be a quadratic function. If I actually go ahead and multiply this out, I'm going to have a lambda squared minus lambda minus 5 lambda, that's minus 6 lambda, plus 5 plus 3 is plus 8. Okay? And that factors nicely in this case, lambda minus 4 times lambda minus 2. And so we can set that equal to 0. We can set that equal to 0. And we get that lambda is equal to 2 or 4. 2 or 4. Okay? So, pretty simple, right? Now, if you have the eigenvalues of the matrix, there must also be corresponding eigenvectors. Okay? There must be corresponding eigenvectors. So let me talk about how to find the corresponding eigenvectors that go with the pairs that we're trying to make here. By the way, one last thing before I leave the eigenvalues behind. This is a nice fact. If you add up the eigenvalues of a matrix, it always adds up to the same thing that the main diagonal of the matrix adds up to. Okay? So this is just, let me just call this up here a quick little fun fact. Actually, I'm going to give you 2 fun facts. Okay. The first fun fact is that if you add up all of the lambdas, however many there are, if you add them all up, in this case there were only 2 of them, but if you add them all up, you get what's called the trace of the matrix. The trace is just this sum of the main diagonals. In other words, it's A11 plus A22 plus A33, etc. Right. Okay. On the other hand, here's a second fact. If you multiply the lambdas, if you multiply these guys together, okay, in this case we multiply, we get 8. Turns out that's the same as the determinant of the original matrix. Okay? So that is actually always true as well. Okay, so the product of the eigenvalues has to be the determinant. So you almost could have come up, for a 2 by 2 matrix, you could almost just use these fun facts to figure out the lambdas. Okay, so you're looking for 2 eigenvalues whose product is 8 and whose sum is 6. Okay, that's what these facts say, right? Well, here you see very quickly that 2 and 4 are the best way to make that work. Okay, so having explained that, we know how to find the eigenvalues. We have to solve this characteristic equation. If it's a 2 by 2 matrix, it's just going to be a quadratic equation, and we know that we can solve a quadratic equation because we have the quadratic formula that will allow us to find those lambdas. Now, if we don't have a 2 by 2 matrix, it can be a little harder. If it's a 3 by 3 or a 4 by 4, your characteristic equation could be a higher degree polynomial where factoring it is not so easy to do. But conceptually, this is just how simple it is. Okay. The factoring the polynomial bit, yeah, that's not really a linear algebra problem to deal with. That's something that we deal with in other places. you're going to have to trust me that I'm going to be giving you problems that are reasonable for you to actually solve the characteristic equation. You just have to trust me that I'm going to give you reasonable things that you can do. How do we find the corresponding eigenvectors? The answer to that is right here in this step that you see that I just circled. Okay? You need to compute the null space of A minus lambda I for each of your individual lambdas. Now, we all know how to find null spaces. So finding the null space of a matrix is something that is up our alley. It's something we know how to do. But we're going to have to do that calculation multiple times. By the way, this null space right here, you're going to have to do it for each lambda, basically. This is called an eigenspace. So let me just emphasize that right here. The null space of A minus lambda I, this is called, okay, I'm just going to erase a little bit right here. This is called the eigenspace corresponding to lambda. Okay? And because it's a null space, it has a dimension and a basis. It's a subspace, right? It's a subspace of Rn. And there's going to be a basis and a dimension for that null space. Okay? Let's try it out on this example that I just worked out right here. We're going to have to verify each of these eigenspaces. We're going to have to calculate each of these eigenspaces. And you just do them one by one. I'm going to start with lambda equals 2. It doesn't matter which one you do first or second. There may be preferences as to which ones to do first or second, and I'm going to get into that a little later on. But let's just try lambda equals 2. So what are you going to do? You're going to try to figure out the null space of A minus 2i. Now, that just means that you're going to go back to the original matrix A, but you're going to subtract 2 from the main diagonal entries. So I'm going to subtract 2, so I'm going to get negative 1. And the other entries stay the same. I'm going to subtract 2 here as well. There's the matrix that we come up with. Now, here's an important point. This matrix that you have here will always be not invertible. Will always be not invertible. Because remember, this lambda, how did we come up with that lambda? Well, we were looking at the matrix A minus lambda I, and we set the determinant equal to 0. So, in other words, when you put in 2 for lambda here, you get a matrix that's not invertible. And you can see that this is not invertible. What that means is you're always going to be able to row reduce it in a way that creates a row of zeros. You can cross off a row, and it doesn't matter which row you cross off in this case. Okay, and then here's another little trick that is really kind of useful. When you're looking for an eigenvector that's in this, okay, so you could think of this as x and y, and you could set y equal to t, and then x would be negative 3t, and then you could bust out the t, right? Well, the point is that so all of your eigenvectors have the form negative 3t, t, where t is in the real numbers. Okay, so basically it's the set of, this is the eigenspace right here, E sub lambda equals 2. That eigenspace is literally just those vectors right there. If I want a basis, all I have to do is bust out the t, and I get negative 3 and 1. The thing I want you to notice is essentially the 1 and the 3, look what happened. We switch their positions. The 3 and the 1 get swapped, and we change the sign of one of those two positions. Okay? This is always going to work, because if you have, let's say you have two numbers a and b here. If you then multiply that by negative b and a, you get 0. In other words, negative BA is in the null space of the matrix. A times negative B plus BA cancels out to 0. Exactly. So there you go. That's the idea. You can always just do that. So in other words, I'm trying to save you some of the tedious ERO work. Just cross off a row, look for a vector by swapping these two numbers and changing the sign of one of them. It'll work every time. Okay, let's try that on the other eigenvalue. Lambda equals 4. That was the other eigenvalue here. So let me just recopy this again so that everybody can see this really clearly. So E sub lambda equals 2 was just the set of negative 3t and t such that t is a real number. Okay. Here's the basis for it. All right. And now let's do lambda equals 4. Maybe I'll come back up here to do lambda equals 4. Okay, so lambda equals 4. We're going to look at the null space of A minus 4i, which means we're going to look at the null space of the following matrix. I'm going to subtract 4 from the main diagonal of my matrix here. So I'm going to get negative 3, negative 3, 1, and 1. Okay. Once again, these two rows have to be multiples of each other because this matrix has to be non-invertible. Okay? And then what I can do for my basis for this particular eigenspace, I can swap these two numbers and then change the sign of one of them. So I'm just going to use negative 1 and 1. Okay? Hopefully this makes some sense. Visually, what's going on, just kind of give you a quick little visual idea of what's really happening here. What we're saying, let me just draw a picture. Because this is a 2 by 2 matrix, right, it's really being applied to vectors that are in R2. Right? You take a 2 by 2 matrix, you apply it to a vector in R2. I can actually draw the vectors. Well, the point is, if I look at negative 1, 1, that's basically this direction right here, right? Negative 1, 1 is right there, and any multiple of negative 1, 1 would be on that line. What we're saying is that if I start with any vector that is on that line, say that's V right there, if I multiply it by this matrix, actually let's just see what we would get. I already know what we're going to get, but let's just verify it. If we multiply this by negative 1, 1, look what we're going to get. Negative 4, 4. So AV is up here like this. It's exactly 4 times V. That makes sense because our eigenvalue was 4. So any vector that is on that line, when we multiply the matrix by it, stays on that line and gets stretched by a factor of 4. This is what we mean by an eigenvector and an eigenvalue pair, right? Everything stays along that line. Now I have another line which corresponds to negative 3, 1. Negative 3, 1 is right over here. We have another line, slightly different direction, but the same idea is going to apply here. If I start with a vector that's along this line, then when I apply the matrix to that vector, you guys can check this. If you take the vector negative 3, 1, and you multiply it by the matrix here, you're going to get negative 6 and 2. It just doubles the length of the vector because the eigenvalue here was just 2. Okay? So that's really the point of the geometry behind what's going on. Any vector that is in this eigenspace gets doubled by the matrix, and any eigenvector that is in this eigenspace gets multiplied by 4 when you multiply by the matrix. Okay? Notice we had a 2 by 2 matrix, and we got 2 different basis vectors. You know, these 2 basis vectors for these 2 different eigenspaces, they could be used as a basis for R2. Right? These 2 vectors, they are Li, they're not multiples of each other. They could be viewed as a basis for R2, consisting of eigenvectors of that matrix. Okay? I know that we always think, well, wouldn't we just use the vectors 1, 0 and 0, 1? There's going to be times when we are going to want to take eigenvectors for our matrix and use those to form a basis. Okay, let's try another example. I want to work on a 3 by 3 example. I think that will be a good thing to do next. So let's just do a similar example here. So here's an example. I'm going to let A be the following matrix here. 3, 0, 0, 0, 2, negative 1, and 1, negative 1, 2. Okay? And I would like to find bases for each eigenspace of A. Okay, I'd like to find bases for each eigenspace. So, first thing I have to do is find my eigenvalues. So I'm going to take the determinant of the matrix that I get when I subtract lambda from the main diagonal. Subtract lambda from the main diagonal. Okay, so this is the determinant that I have to calculate. What you want to look for here, guys, is a good row or column to cofactor expand. I know we have an arrow method for a 3 by 3 determinant, but if you try to use the arrow method here, you really are going to get a cubic polynomial that is hard to factor. Remember, this is what I was talking about earlier. Factoring the characteristic polynomial, it can be difficult. It will be easier to do it if the matrix is nice in that there happens to be a nice row or column. In this case, the first row is very nice, right? I can expand along the first row, and I'm going to get 3 minus lambda times the determinant of this little 2 by 2 submatrix. So that's 2 minus lambda times 2 minus lambda, and then minus 1. The reason that that is so nice is that it's already partially factored. It's partially factored. So what I can do is I can now take, I don't want to multiply it all out, or I'll end up with a nasty cubic equation. I want to leave it with the 3 minus lambda factored out. And now the part in the parentheses here, lambda squared minus 4 lambda plus 3. Okay? This is just a quadratic, and it actually factors very nicely. So I'm just going to do it. It's going to be lambda minus 3 times lambda minus 1. And if I set that equal to 0 now, I'm going to find that lambda is equal to 3 or 3 or 1. These are my lambdas. I want to write down the repeats. If there's a same lambda more than once, then I want to write that down. In fact, what we're going to say here is that this lambda equals 3 has weight, I'll call it the weight, or multiplicity is a fancier word for it, of 2. It's just the number of times that that lambda shows up as a solution to the characteristic equation. Okay? We do need to keep track of that. All right? Just as a quick test, if I add up my lambdas, 3 plus 3 plus 1 is 7. That agrees with 3 plus 2 plus 2, which is 7. That's the trace of that matrix. Okay? And I'll leave it to you to check that this matrix has a determinant of 9. The product of these lambdas is 9. Okay? So that's a good way to kind of check yourself. So we have 2 different lambdas to worry about. Here is a quick tip. Here is a quick tip about finding the eigenspaces. For reasons that will become clear later, fairly soon later, my tip is that when you have repeated lambdas, lambdas of multiplicity, right? Multiplicity in this case 2. When you have eigenvalues of multiplicity, you want to work on those eigenspaces first. Okay? We want to do those first. So work on the eigenspaces, E spaces, with lambdas that have multiplicity first. there's multiplicity, if there are repeats, you want to do the repeats first. Okay? I'm going to erase the calculation of the eigenvalues now. Of course, you can always rewind this and look at it again if you need to. But we're going to just get right into calculating the eigenspaces. And I'm going to start with lambda equals 3 because it's the one that had multiplicity. There was a repeat there. Sometimes there won't be any repeats. All the lambdas could be distinct. But when there are repeats, please take my advice to heart and work on the eigenspaces of the repeats first. Okay? So let's try lambda equals 3. I'm going to look at the null space of the 3 by 3 matrix when I subtract 3 from the main diagonal. When I subtract 3 from the main diagonal, I'm going to get this matrix right here. Okay? As expected, this matrix is not invertible. Okay? You can very quickly see that essentially you have 2 pivots here, more or less. Okay, I didn't really row reduce it, but you can see what's going on there. So what you can do now is start setting up your free variables. Let me just use x, y, and z for the 3 columns here. So z is free. I'll call it t. And then from this middle equation, you can see that the y and the z have to have opposite signs, right? So y would be negative t. And then based on that, the x, as it turns out, has to be 0. Okay? It has to be 0. So there you go. Your basis for this eigenspace is just literally x is 0, y is negative 1, and z is 1. You just bust out the t, as usual. So this is the basis for E sub lambda equals 3. Okay? Now what I want you to notice here, this eigenvalue, remember the eigenvalues here? We had lambda equals 3, 3, and 1. The multiplicity of the eigenvalue 3 was 2. 2 times, right? 3 shows up 2 times. But look at the dimension of the eigenspace. The dimension of the eigenspace corresponding to the eigenvalue 3 was only 1. It was less than the multiplicity, the number of repeats of that lambda. Because the multiplicity was 2. There were 2 repeats, but we only got 1 eigenvector. That is bad. Okay, that is essentially what I'm going to call a defective situation. A matrix is defective if one or more of its eigenvalues fails to pull its weight. The eigenvalue has a weight of 2 and only gave us 1 eigenvector here. Okay, so that's an issue. And this is why, if I ask you if you have a matrix that is defective or not, I'll write down what defective means formally in a minute. But if I ask you, is this matrix defective, right? The reason you want to work on the eigenspaces for the lambdas that have repeats is that those are the lambdas that might not pull their weight, right? They might not pull their weight, as we see right here. So we could already say that this matrix is defective, okay, before we even spend any time looking at the other eigenvalue. You might be wondering, maybe this other eigenvalue, we haven't done that yet, maybe this other eigenvalue could save us here. Let's look at lambda equals 1, okay? The matrix is defective, I've already kind of said that. But let's look at the situation with the other eigenspace. I'm going to subtract 1 from the main diagonal here. Subtracting 1 from the main diagonal, I'm going to get that matrix right there. Okay. And what you'll notice, this isn't quite in row echelon form either, but essentially, here's the thing. The first 2 rows are already good.